Hello everyone, welcome back to my YouTube channel. My name is Sarita from Sri Venkateshwara College of Engineering, Bengaluru. In this video, I am going to discuss about Poisson distribution, which comes under Mathematics 3 for Computer Science and Engineering stream. Now, let's get into the topic. A Poisson distribution is a discrete probability distribution. It gives the probability of an event happening a certain number of times, which is k, within a given interval of time or space. The Poisson distribution has only one parameter, that is lambda, which is the mean number of events. The graph below shows the examples of Poisson distribution with different values of lambda. We can see the graph here, the Poisson distribution graph for various lambda values, that is 0.5, 1, 2, 3, 6. And the probability here in y-axis, and the lambda values which is under x-axis. So here the main contents are: what is Poisson distribution, examples of Poisson distribution, probability mass function graphs, mean and variance of a Poisson distribution formula. What is a Poisson distribution? Poisson distribution is a discrete probability distribution, meaning that is it gives the probability of a discrete outcome, that is a countable outcomes. For a Poisson distributions, the discrete outcome is the number of times an event occurs, represented by k. You can use a Poisson distribution to predict or explain the number of events occurring within a given interval of a time or a space. Events could be anything from a disease cases to a customer purchases to a meteor strikes. The interval can be any specific amount of time or space, such as 10 days or 5 square inches. So you can use a Poisson distribution if the individual events happen at a random and independently. That is, the probability of one event doesn't affect the probability of another event. You know the mean number of events occurring within a given interval of time or space. This number is called lambda, and it is assumed to be a constant. When events follow a Poisson distribution, lambda is the only thing you need to know to calculate the probability of an event occurring a certain number of times. Now, take an examples of Poisson distribution in general. The Poisson distribution are often appropriate for count data. Count data is composed of observations that are non-negative integers, that is the number that are used for counting, such as 0, 1, 2, 3, 4, and so on. Horse-kick deaths. One of the first application of the Poisson distribution was by statistician Ladislas Borchesvius. In the late 1800s, he investigated accidental deaths by horse kick of soldiers in the Persian army. He analyzed 20 years of data for 10 army crops, equivalent to 200 years of observation of one crops. The following histogram shows a simulated data that are similar to that Borchesvius observed. He found that the mean of 0.161 soldiers per crop died from horse kick each year. However, most years, no soldiers died from horse kicks. On the other end of the spectrum, one tragic year there were 4 soldiers on the same crops who died from horse kicks. So, using a modern terminology, the deaths by the horse kick is an event. The time interval is 1 year. The mean number of events per time interval is lambda is 0.61. The number of deaths by horse kick is in a subsequent year is k. The army crops that Borchesvius observed were a sample of the population of all Persian army crops. Because of the random nature of the sampling, samples rarely follow a probability distribution perfectly. The deaths by horse kick in the sample approximately follow a Poisson distribution, so we can reasonably infer that the population follows a Poisson distribution. And the other examples of Poisson distributions are, since Borchesvius' time, Poisson distribution have been used to describe many other things. For example, a Poisson distribution could be used to explain or predict text messages per hour, male grizzly bears per hectare, machine malfunctions per year, website visitors per month, influenza cases per year, so etc. Probability mass function graphs. Probability mass function graphs. A Poisson distribution can be represented visually as a graph of the probability mass function. A probability mass function is a function that describes a discrete probability distribution. The most probable number of events is represented by the peak of the distribution, the mode. When lambda is a non-integer, the mode is the closest integer smaller than lambda. When lambda is an integer, there are two modes, lambda and lambda minus 1. When lambda is low, the distribution is much longer on the right side of the its peak than its left. That is, it is strongly right skewed. As lambda increases, the distribution look more and more similar to a normal distribution. In fact, when lambda is 10 or the greater, or the normal distribution is a good approximation of the Poisson distribution. We can see in this graph how the Poisson distribution is similar to the normal distribution when lambda is increases. The next is the mean and variance of a Poisson distribution. The Poisson distribution has only one parameter called lambda. The mean of the Poisson distribution is lambda. The variance of a Poisson distribution is also lambda. In most distributions, the mean is represented by mu and the variance is represented by sigma square. Because these two parameters are the same in the Poisson distribution, we use the lambda symbol to represent both. The next is the Poisson distribution formula. The probability mass function of the Poisson distribution is P of x is equal to k is equal to e to the power of minus lambda, lambda to the power of k divided by k factorial, where x is a random variable following a Poisson distribution, k is the number of times an event occurs. The P of x is equal to k is the probability that an event will occur k times. E is the Euler's constant, approximately 2.718. Lambda is the average number of times an event occurs. The factorial symbol is the factorial function. Example, by applying the Poisson distribution formula, an average of 0.61 soldier died by horse kicks per year in each Persian army corps. You want to calculate the probability that exactly 2 soldiers died in a 7th Army Corps in 1898, assuming that the number of horse kicks deaths per year follow a Poisson distribution. So when it comes to calculation, the Sapsik Army Corps in the 7th Army Corps and the year is 1898 don't matter because the probability is a constant, where k is equal to 2, the deaths by horse kick. The lambda is 0.16, that is the deaths by horse kick per year. And E is the constant 2.718. And P of x is equal to k is equal to e to the power of minus lambda into a lambda to the power of k, all divided by k factorial. We can substitute the E value, lambda value and the k value. The E value is 2.718 and the lambda value is 0.16 and the k value is 2. By substituting these values, we can get the P of x is equal to 2, that is equal to 0.101. So the probability that exactly 2 soldiers died in the 7th Army Corps is in 1898 is 0.101. Thank you. Please do watch the video and subscribe the channel.